we know what derivatives are. Now we want to apply derivatives. Okay? We know what derivatives are. Now we want to apply derivatives. And the first application comes with minimum and maximum values. Remember that day I had you in class and I told you about my teacher, professor one day in college? He showed us how a doctor came to him and asked about a branch onto an artery. Remember I showed you that? Real quick. He worked at the Mayo Clinic, and his job was just to help doctors solve problems. Doctor came in one day, said, "I'm doing a bypass." He said, "Great." He said, "Well, what I need to do is, as I put the bypass in, so there's a blockage in the artery, I'm going to put a bypass in." He said, "At what angle do I make the bypass in order to minimize the viscosity of the blood flow or the friction of the blood flow?" That's a big question, right? That's an important question. Like that saves lives, right? So notice the key word: minimize the viscosity of the blood flow. He did an application of derivatives that actually a very similar problem pops up in chapter 4.7 for us that we'll see in a month. So that's a big deal, right? Calculus saves lives. That's what you need to know. So absolute maximum and global maximum. We will use the term absolute maximum. And on this graph, an absolute maximum refers to the highest value, y value, range value that the graph achieves. What is the largest y value that this graph achieves? So 64, and that happens at an x equals value of 4. What is the absolute minimum? Negative 152, and that happens at an x value of negative 1. Now, honestly, absolute. Oh, sorry. I'm over here, it looks like. Thank you. All right, so from in calculus, we're generally more concerned with local mins and local maxes. And you'll hear that term all the time from now on moving forward. And a local maximum, relative maximum, means it's bigger than everything else immediately around it. Immediately around it. Okay? So is there a value up here that's bigger than everything else immediately around it, but not necessarily absolute? Yeah, you can tell right there. So value of 37 at x equals 1. Ugh. How about a local minimum? Negative 27 at an x value of 3. Is the height of negative 27? There's another one. Negative 152 is also a local minimum at an x value of negative 2. So a local maximum or a local minimum can also be a absolute maximum or absolute minimum. Okay, so we did example 1 together. A guy by the name of Fermat, important guy in mathematics. His most popular theorem is this: a squared plus b squared is c squared. You don't have to write this down, but anybody know integers that satisfy that? Integer values that satisfy the Pythagorean theorem? 3, 4, 5, 6, 8, 10, 5, 12, 13, 7, 24, 25, 8, 15, 17. The list goes on and on, right? Fermat said that if you increase the degree to another integer that is greater than 2, so say 3, 4, 5, so on and so forth, some n power, that there are then no integer solutions. It may not seem like that big of a deal, but he wrote this, and unfortunately he didn't complete the work, and some of his work got lost, and so they call it Fermat's last theorem. It was what he kind of finished up before he passed away or whatever, and it was left unsolved for 400 years. Back when I was in high school, a guy finally solved it after about 10 years of work. He was given like $10 million Nobel Prize. Good stuff. So one thing he wrote about calculus is this: if f has a local maximum or minimum at c, and if the derivative at c exists, then we can make a conjecture. So you guys tell me, does the derivative exist at 1? Yes. Does the derivative exist at 3? Do I have a local max or local min? Do I have a local max or local min? Then what's true about the derivative at those spots? What else? The derivative is, give me a value, 0. F prime of c is equal to 0. So most of the time when we find local maxes and local mins, we set the derivative equal to 0 and find it. So these are critical numbers of a function f, a number c in the domain of f such that either f prime of c does not exist or f prime of c is equal to 0. Those are the two situations we'll look at on the next page. Go get some brain food, come on back, ready to go, and we'll have a great day in calculus. Sam Moyer, hope you're having a good time. Bench warmers, hilarious. Okay, flip it over. Suppose you have the derivative equal to 0, and you have a local max and a min. That's one example where you would be looking for and finding critical points. But it doesn't always end up having to be a local max or a min. For example, a cubic has a derivative equal to 0 at 0, but yet that is not a local max or min, is it? So doesn't just because you get a derivative equal to 0 doesn't mean you have to have a local max or min. There's a good chance you might have one. So that's really a derivative equal to 0. There's a lot of examples here. If you end up with f prime of c does not exist, and so an undefined function, say you have 1 over x minus 1, you know that that is undefined for a value of 1, and so therefore, when you find the critical point would occur at x equals 1. You can also have another example where you would have a critical point, and that would be on a function that has a corner. So the function y equals the absolute value of x, what shape does the absolute value of x be? It's a v. Why does the derivative not exist at x equals 0 for that spot? Okay, so Kyle is definitely stating that correctly. To use the mathematical term, we'll say that the derivative from the left is -1, and the derivative from the right is +1. Those don't match, so therefore the derivative does not exist. The derivative does not exist at 1 here because the function is discontinuous at 1. You can't have a derivative at a discontinuity. And finally, a vertical tangent. Suppose you had y is equal to x to the 1/3. As you graph that, you get this kind of shape. And you can see that you would get a vertical tangent. What is the slope of a vertical line? Good try. Undefined. Um, and undefined is not a value that we can't ascribe value to undefined. So therefore, vertical tangent, you would have f prime of c, the derivative would not exist. So let's practice actually finding critical numbers of a given function. Then you can work on an assignment. Um, yeah. Just to give you an idea, this weekend, as I told you, I spent another 3.5 hours or so mapping AP Calculus topics and stuff. And as I was doing so far I've put together about for chapter 2 so I've pulled from 3 tests so far: 2012, 2008, 2003. Out of all those test questions, 45 test questions for each one, 135 test questions overall, I have 4 questions that come from chapter 2. I have 30 that come from chapter 3. And I have 48 that come from chapter 4. So this is a very, chapter 4 and 5 are definitely the heaviest chapters regarding content for the AP exam. So find the critical numbers of the function. How do we find it? We take the derivative and we set it equal to 0. So f prime of x is equal to, what's the derivative? 3x squared minus 4x plus 1, and we set that equal to 0. Does it factor? 3x and x. Minus 1. So we have 1/3 and 1. So we know where the derivative is equal to 0, so it has critical values at 1 and 1/3. The question is it is there anywhere where the derivative does not exist? That means, are there any domain restrictions for this polynomial? No, you can plug in any number you want for a polynomial, right? So we don't have to worry about that. Okay, so x is equal to, oh, stupid computer. Okay, x is equal to 1/3 and 1. If you want to write C for critical number, that would be fine too. For B, when I take the derivative, what would you have to use? Yep, the quotient rule. Yep, these are the critical numbers. You love this problem. Great. Oh, the one before it. Nice and simple. All right, great. Well, this one isn't too bad either, but I don't want to use the quotient rule here. I want to just rewrite it as x minus 1 over x. You see how I did that? So all I did is take x squared divided by x to get x, and then 1 divided by x to get 1 over x. Okay, we'll write it out. I separated it into two fractions. X squared divided by x is x over x. That's a nice way to rewrite it, and that way I don't have to use the quotient rule. F prime of x is equal to, what's the derivative of x? 1. What's the derivative of negative 1 over x? So you have x to the negative 1, drop the negative 1 in front, it turns to positive, and then decrease the exponent by 1. Now, this is your derivative. Is there any spot at which that is undefined? 0. So x equals 0 is one spot where the derivative does not exist. Okay? Second of all, if you want to simply plug in 0 for the derivative and solve it, I'm going to subtract 1, and I'll cross multiply. I get a negative x squared is equal to 1, or x squared equals negative 1. What's the solution for x squared equals negative 1? Plus or minus I, and those are not real. So there is no point at which the derivative is equal to 0 for this function. So our only spot where there was a critical value was where the derivative, where the derivative was undefined. That was for next values. Yeah, the fact that it comes up in the original problem would give you an indication it would be in there as well. But you'll see that in D, that's not the case. Yeah, you need to look at the derivative. So here's the deal, Hannah. You can't plug in 0, right? So therefore, it's a critical value. Yes. The definition of a critical value is where the derivative does not exist or where the derivative is equal to 0. Now, you guys, I will be honest, okay? Your book will not list 0 as one of the values. And this is why. Is 0 part of the original domain? Can you plug 0 into the original function? No. So any value you can't plug in the original function, you're not going to be able to plug in the derivative, and that would make sense, right? They wouldn't even list 0 as a value. But you'll see that play out in letter D. Don't worry about that. I'm not going to be critical of that on your test. F of x is equal to the absolute value of 3x minus 6. What does that graph look like? Over the right, how many? Nope. 2. What would you plug in to get 0? 2. Okay, and so this has, it looks like 3x minus 6 for some values and negative 3x plus 6 for other values. So this is what the graph looks like. It's an absolute value function shifted to the right 2 units. So instead of solving this algebraically, I'm going to look at it graphically. Okay, if you were to take the derivative of 3x minus 6, what would you get? 3. Is 3 ever equal to 0? No. Take the derivative of negative 3x plus 6. What do you get? Is negative 3 ever equal to 0? So the derivative is never equal to 0. However, is there a spot where the derivative does not exist? What spot is that? Yeah. So that's my critical value because the derivative does not exist at x equals 2. It is a corner. And finally, for the last example, D, we can rewrite this as x to the 3 halves minus 2x to the 1 half. And in order to find the derivative, I'm going to find the derivative and then set it equal to 0. We'll look for critical values here. Move the 3 halves in front. I get 3 halves x to what power? We'll call it square root of x. What's the derivative of 2x to the 1 half? So, is there a spot where the derivative is undefined that the function was originally defined for? Yeah, here, can you plug in 0 to the original? What do you get? 0. But can you plug in 0 to this? No, because you would get undefined. Nope. If you bring the 1 half in front, it's still negative, right? So therefore, I drop it to the denominator. So negative 2x to the 1 half. Bring the 1 half in front. So when you take the derivative, negative 1 half times 2, x to the negative 1 half. So that gives me a negative 1 and x to the negative 1 half, square root of x. Okay, so so we know that we have this spot, x equals 0, because you can't plug in 0 there. And then we also have where it's equal to 0. Somebody tell me how you might solve that equation. Ooh, no thoughts. Okay. Okay, sure, let's do that. We'll multiply top and bottom by the root of x. And if you do that, you get 0 is equal to, so top and bottom by the root of x, I'll get 3x over 2 roots of x, right? And then I'll multiply top and bottom here by, to get common denominators, multiply top and bottom by 2. So I have a common denominator here. So this is 3 roots of x over 2 minus 1 over x, or root of x, right? I multiply the top and bottom by the root of x, get that. Multiply top and bottom by 2 to get this. Okay. So 0 equals 3x minus 2 over 2 roots of x. So you can see that again, x can't be 0 in the denominator. True or false? If the top is equal to 0, then the whole thing's equal to 0. True. Where's the top equal to 0? You set the top equal to 0, you get 2/3. Take out your graphing calculator. Square root of x to the third minus 2 roots of x. And I'm going to zoom standard. And that's the graph. So let's look at the graph and determine if it seems that we have critical values at 0 and 2/3. Okay, does it seem to make sense that we have a critical value at 2/3? Why? Because the derivative is 0. Good. Does it seem like we have a critical value at 0? Why? Two reasons. Number one, it appears that the slope will be a vertical line. And second of all, this would be an endpoint, wouldn't it? Right? And so it seems like you would have that issue as well. So 2/3 and 0, that is your answer. What is the x value? Yep. So an x value of 2/3, the derivative is 0. Okay, time for you to practice some problems. Oh, whoop, that's college algebra. That is not yours. This is yours. There you go. 441, page 230, numbers 31 through 40. Sam Moyer, we hope you had a great time at college, and we hope to have you back. And we're going to quote bench warmers every day now, because that's what I watched last night. I think if you did an IQ test for me before and after the movie, I think it would have dropped.